Now we're going to see what it looks like to use IDA free for analyzing the Binary Bomb Lab Phase 1. So first of all, for the code for your class, inside of that folder, there's a Binary Bomb Lab, and you choose Windows or Ubuntu, depending on what you're using right now. I'm using Windows, so I'm going to copy the bomb and the bomb.pdb file onto my desktop. Then I'm going to go ahead and open up IDA freeware and click New to disassemble a new file and select the copy of the bomb lab, which is on my desktop. Hit open. It's going to have all the default analyzers. Just accept the defaults and hit OK. And then it's going to ask you, do you want to use the PDB file, which it is found at some particular location. That's the original compilation location, so it's not going to actually be there. But it's still going to be able to find the bomb.pdb that's just in the same directory. So go ahead and hit yes on that. Now, if you're doing it as the advanced version where you don't use the symbols because you want to, challenge yourself, then you should hit no, and also don't copy the PDB file out. Because PDB file is all the symbols, it's the names for functions, and it makes it easier to analyze. And you won't have PDB files, you won't have symbols for most real things that you need to reverse engineer, unless it happens to be something from Microsoft where they provide symbols to the public. Okay, so we're in IDA, and the first thing we see is a jump to main. So let's go ahead and do that. And then here we immediately see the benefit of using a tool like IDA, and that's the control flow graph. Right, so we have this nice graphical view instead of just, if I hit space, I see just the linear disassembly where it just goes top to bottom. And although the linear disassembly has little hints on the side for like arrows and stuff for where jumps are going to go and that sort of thing, it's much easier to follow that sort of thing in the control flow graph view. So control flow graph is the nice thing. Now, when you're doing this bomb lab, the whole point of the bomb lab is to figure out what are the inputs supposed to be. And we can confirm that if we go ahead and run a command prompt, go to the desktop, and just execute the binary bomb. Run the bomb.exe, you get welcome to my fiendish little bomb. You have 6 phases with which to blow yourself up. Have a nice day. And then it's sitting here blinking as if it's waiting for some sort of input. And so I'm going to go ahead and give it some input, and then it says, boom, the bomb has blown up. So I'm putting some sort of input in, and then it blows up. So I want to find what inputs can cause it to not blow up. And to do that, I'm going to have to use reverse engineering and reading the assembly. Now, the trick about reading assembly is that you need to take what you already know about the details of how assembly works, and you want to skim the code as best you can. So I kind of view it like if you were reading a foreign language. When you first start out with a foreign language, you sound out every syllable. Essentially, each assembly instruction is a syllable, and you're sounding it out if you're reading, okay, this does this does that. But as you become fluent in a language, you try to just, pick up the words and the sentences, and you read faster and you skim more, and your eyes just sort of intrinsically see things. There's, examples where people mess up the order of letters inside of English words, but your eyes just automatically, skip that, and your brain just corrects it, and you still read it as the correct word, even though it's not actually the correct letters in the correct order. It's because your brain is looking for some pattern recognition. Well, the same sort of pattern recognition applies here. So for instance, I can see patterns like, okay, there's moves from certain registers into memory addresses, and I can know something about the pattern of Microsoft compiled code using a shadow store to save registers. There's patterns like if I see pushes at the beginning of the code, and I check down at the bottom and I see balanced pops at the end of the code, well, then it's balanced as all things should be, and that means that I'm seeing some sort of callee save registers being used. Then there's patterns like seeing subtract from the stack pointer at the beginning. That's saying some sort of allocation of local variables. And also we learned about the pattern of this repstos. The repstos with the C's, that had to do with some debugging initialization that was done by default if you don't turn it off for debug builds. And so immediately here within the first few, assembly instructions, I can infer that this is a debug built executable. Now, if the PDB wasn't proof enough, maybe you were missing the PDB, you would still know based on the assembly that was generated, this is a debug built executable. And then, of course, there's helpful things like this call to a function called check for debugger, just my code. Well, so that's all nice and fine, but that doesn't really help me with my goal. And my goal is I want to figure out what kind of input I could give to this thing so that it does not print boom. So I need to find where it does print boom, and then I want to avoid that. So the key thing about this sort of challenge, about reverse engineering in general, is that usually you always start out not knowing anything. And so you want to mix your skimming at a high level with your diving deep. So basically you want to do some sort of skim, like just kind of get the broadest perspective you can, just like skim over all of the control blocks. Is this a giant function? Is this a tiny function? If I click into some other functions, are those giant functions? Do they look like they have some sort of switch statement in them? Like all sorts of things can be derived from that. Now, normally one of the very first things that you're recommended to do is to look at things like strings, because debug strings, as you can see helpfully displayed here, I don't even have to go into a strings window. It prints the strings right here for my benefit. But still, one of the first things you're always recommended to do is pull up a strings window. So let's go ahead and do that. We go to View, Open Subviews, and then Strings. All right, well, I'm not sure why that came up empty to start with, but once we close out the window and reopen it again, we get our list of strings. So you can see some things like the string that we actually see, specifically at the beginning, the welcome to my fiendish little bomb, you have 6 phases with which to blow yourself up. Then we also see encouraging strings like phase 1 diffused, or that's number 2, keep going halfway there, and so forth. We can also see strings like CMU domains, because this binary bomb originally came from Carnegie Mellon University, and they would submit the answers to an online server so that the instructors could see data about how many times someone actually tried it. But yeah, so you always want to just skim through the strings because they can give you information that's printed out. They can give you things about error message. They can also give you things about particular functions that are called, get current process, terminate process, and so forth. And knowing which functions are called can tell you things about what sort of functionality it has, like does it, connect to a network server? Maybe there were no explicit, host names in there or anything like that, but you would still see if it connected to a network server based on the functions that are called. All right, well, anyways, once you have fun looking through the strings, then you come back to the actual code, and we can see in here, and I accidentally clicked something. So as a reminder, we've got the little arrow going back right there, upper. This is our navigation forward and backwards. So let me get back into main. And so we could read, all of this, but like I said, we always start with a skim. So we keep skimming down and we ultimately find, these interesting strings that we had already seen printed out. And so this tells us, okay, I don't really care what's going on up here. I definitely know that it's getting here. So let's start our reading from here. We have things like call to initialize bomb. We have these printfs, and then we have a function called readline that correlates with what we saw when we actually ran the thing, that it looked like it was blinking and waiting for some input. We gave it input, and then it just blew up. So after the read line, we get down to this phase 1 and a phase 1 diffused. So a reasonable guess might be that we want to hit phase 1 diffused in order to avoid that boom, the bomb has blown up. So how do we get to phase 1 diffused? Well, it's going to return back from phase 1 and then immediately call phase diffused. We could go in here and take a look at phase diffused and see what kind of stuff is going on here. Does it actually have the bomb or anything like that? Well, I don't see any boom, you blew up. So I'm going to go back and see what's actually happening in phase 1 instead. If I go into phase 1, then here I'm going to see, some strings helpfully shown, but I also see a call to explode bomb. So again, it's always going to take you longer to just, eyeball everything and see the things that pop out. I just can't help but see the things that are obvious jumping out, but call to explode bomb, that's very clearly something I want to avoid. And with this control flow graph view, it's clear that there's one path around that and there's one path through that. So I got to figure out how to avoid it. And it looks like how to avoid it has to do with this jump Z, jump if zero. Zero flag is set if the result of some previous operation is equal to exactly 0. What's the previous operation? Well, it's a test on EAX. As a reminder, test is behind the scenes really just an AND instruction that throws away the results after it sets some flags. So it's doing AND EAX with EAX, and if the result is 0, then it jumps forward to here. So you can see that that label is saying jump to here if the result is 0. Otherwise, if it doesn't take the jump, it's going to fall through. And again, we can press the space bar to go into the linear disassembly view, and we can see that the fall through is falling through from if the jump's not taken, fall through to call. Otherwise, the jump is taken and it skips over the call. Okay, so we want to not hit explode bomb, which means we want this to be true, the jump 0 to be taken, which means we want the EAX to be 0, and EAX, as we recall, is the return register after we call into a function. That's where the return value is returned, RAX or EAX in 32-bit code. So here it's just checking the bottom 32 bits, so you could have a 64-bit return value, but it only cares about the bottom 32 bits, and it says if those bits are 0 and 0 and 0 equals 0, then it's going to jump and avoid the bomb. So the thing immediately before that is strings not equal. So somehow we need to get this strings not equal to return a value of 0. Now at this point we could jump in here and look at strings not equal and go analyze it, but this is essentially the essence of effective reverse engineering. It's a combination of making educated guesses and trying to read code like a native speaker and not sound out every single syllable, but make informed guesses and skim wherever we can. Go deep, go broad, go deep, go broad. So here we want to stay broad for a second. It's very tempting to always go deep and to just always, read and, analyze every single thing. But if we back up for a second and we start looking at the beginning of the function, and we say, what does this function do? Well, we can see, typical things. We can see, again, that sort of initialization for debug stuff, and we can see this for debugger, check for debugger just my code. So I can infer that all of that kind of stuff is all just boilerplate stuff that is a debug-built binary. We'll just have that inserted by the compiler, and I probably don't need to care about that much. So that's just all sort of cruft that I don't care about. Allocation of local variables, I might care about that. Pushing some callee save registers, things like that. I probably don't care about that. That's just something the compiler makes it do. So that means the real code is really just this stuff right here. So it's this movement of something, this LEA, this load effective address, get the address from something and put it into RDX. And then a move of some particular memory location, we can see it's RBP plus something. So we can infer that this is probably some local variable. It's a RBP relative local variable. So IDA helpfully says this is the arg0, and so it's probably the argument 0 to this function. So the 0th argument to this function is placed into RCX. So basically, we've got a situation where there's a call to strings not equal, and there's two parameters being passed. We know that because we remember our calling conventions from Windows means that the first parameter to a function is going to be an RCX, second parameter is going to be an RDX. So what are these two parameters? Well, we don't know what that is, but IDA very helpfully tells us that this parameter right here is actually an address of some string. So we could double click on that. We would see that this is actually some address in the RData section of the executable. You're not expected to know what different sections of executables mean yet, but essentially this is just some global data. So it's basically like there's a global string, and the literal string is, I am just a renegade hockey mom. So if we go back, we're essentially seeing a pointer to a string, I am just a renegade hockey mom, and something else coming out of a local variable being passed to a function called strings not equal. And this is where, again, we want to make educated guesses, and we might guess that this is going to be some sort of input that's being compared against this string, and it's checking if the strings are not equal, then it's going to return one thing, and if the strings are equal, it returns something else. So that's our inference, that's our guess, and the nice thing here is we have a debugger, so we don't have to do just pure static analysis. We don't want to do pure static analysis if we don't have to. It's always easier to understand what this code is doing, what this argument is, if we actually look at it at runtime, because right now, we don't know what it is and we can't know what it is. We have to execute this thing to see what's going on. So let's go ahead and start this bomb executable in the debugger. So we go up to debugger and we just go ahead and select start process. Now it's going to say, hey, if this thing's malware, you could totally screw up your machine. So are you sure you want to run this? And yes, in this case, we know it's not malware, so we do want to run it. So this starts the executable, and you can see it already has run the executable because I don't have any sort of debug breakpoints or anything like that. So if I put an input now, it's just going to continue on, and I won't get a chance to stop and see what's going on. So first, I need to find my location, get back to location, set a breakpoint, and then provide some input and see if I can find where the input is actually being used in the program. So at this point, I can press G in this view to jump to an address. I'm going to type in, let's type in phase 1 instead of main. Let's go ahead and go right to phase 1. Here's phase 1. I can see it in a nice control flow graph view. Obviously, I didn't set up my IDA the same way you're supposed to from the actual IDA class yet. But yeah, so I want to set a breakpoint before this call to strings not equal because I want to examine these two registers. So I'm going to just right click there and I'm going to add a breakpoint. Now I can go ahead and provide some input to this thing. Not that one. I'm going to go ahead and close that one. This one, which is the one actually run by my debugger right now. So I'm going to type my input and hit enter. Now it goes back to the execution and it's going to say like, hey, I can see based on that PDB file that like the actual, source code name of this particular thing that I want to show you is source phases.c, and I can't find that at this path. That all the actual paths where the thing was compiled, those are baked into the PDB file so you can do source level debugging. Well, I didn't give you the source on purpose, which means you're not going to be able to find the source, so just go ahead and hit cancel. Now at this point, it is broken in the debugger at this call. And so we can take a look at RCX and RDX. Well, RDX is just the hard-coded thing, so that's always the same. But RCX, if you mouse over it, you can see there that it's saying that it's actually input. So if I go ahead and look at RCX in my registers window, and there's this little arrow, and I say jump to that, then here we go. That's the actual stuff. And at this point, I can actually hit A to say display it as an ASCII string instead of bytes. And indeed, it shows that it is my input, and 0. And if you're really unsure that it's your input or not, just give some crazy input, not some just generic string like that. That could be, a false lead, a red herring. But yeah, that's my input. And so what I have is my input being put into a register, RCX, and some other hard-coded pointer to a string being put into the register RDX, and they're being passed into a thing called strings not equal. So if I now go ahead and step over this call, and again, I haven't initialized everything correctly yet the way you do in the class, so I'm going to add those debugger commands. And so basically, I want to step over the call instruction and see what EAX is at the end. So I step over, and right now EAX is 1. So strings not equal returns 1 if the strings are not equal. That makes sense. So basically, if we pass two strings that are equal, it should return 0, and 0 is what we want. We want test 0 and 0 to be 0, jump 0 to jump, and then skip over this call to explode bomb. So I can see that if I just hit play right now, then it just terminates the process. So I want to try this again, and I want to give this string, I want the strings not equal to return 0. So let's try that string. That's my hypothesis. Let's investigate. Go ahead and hit play in order to start the debugger, and then paste in this particular string, hit enter. It's still going to fire at this particular breakpoint, and now once again we can just step over it. And what is the result in EAX? It is 0. So you can see it there, you can see it here. And so I have found the correct input in order so that if I step, now I took the jump and it skipped over the explode bomb. And that means I can continue my analysis. And that's exactly what I want you to do in this class. I want you to keep analyzing and figure out, now that you have a sense of how to look around through the assembly, figure out what this binary wants. What does it want? How can you get through all of these phases without exploding the bomb? So there's only one last thing that I have to tell you before I let you loose on it, and that's that this particular executable takes a file as input as well. And if you had read all of this code, you would see that there's things pertaining to do with file opening like fopen. And if you read and squinted your eyes and you did some analysis for a while, you would realize that that's doing an fopen on your arg0. So basically arg1, the 1th argument on the command line, which is not the bomb.exe, which is the 0th one, but actually the first parameter to bomb.exe. So it opens a file at the arg1 and argv of 1, and that is going to actually be a solutions file. So in order to stop you from having to paste in the solution every single round, you can create a file and pass it in as the first argument that has all of your correct solutions. So let's go ahead and open Notepad. Let's go ahead and paste in our solution, and you need to have an actual return. You need to have a new line at the end, and you need to have a blank line here. I'm going to save this as a.txt, going to save that to the desktop, so it's just relative path relative to the bomb.exe. And so now what I can do is I can go ahead and go to my debugger. Oh, let me stop my debugger first. Go to the debugger, select process options, and then just do /a.txt, and that will give you the bomb.exe with the first parameter as /a.txt, and it's going to open that with fopen and feed in the answers. So if I do this, now I hit play, we will see that it immediately breaks here, and we will see that immediately I have something in RCX. And so let me go there to RCX. You can see that it actually got broken. I probably put some sort of special character in here or something because of my pasting incorrectly. So I'm going to fix that quick and then bring it back. Oh, no, sorry, never mind. It's just that it actually, for whatever reason, it's probably because I had already interpreted that as a string before, but the string was just input length long. And now I need to undefine this. So I hit U for undefined, and now it's back to all just bytes. And now I hit A again to turn it into an ASCII string. And now it's the full proper length ASCII string. So, all right, the input is good. That's all good. Now go back to my actual code. And I can step over, and what I want to do now is I want to hit G, and I actually want to go to phase 2 and set some sort of breakpoint here. So I'm going to go ahead and right-click and add a breakpoint, and then I'm just going to go ahead and hit Go, Continue, and we can see that it says phase 1 diffused. How about the next one? And here again, I need my input of some sort, and then we have to go debug our way and figure out what's going on in the code. All right, that's it for me. That's my just little brief introduction to this reverse engineering exercise. Now it's up to you to make your way through the rest of the binary bomb.